Welcome, everyone. I'm excited to be hosting this important seminar for you today. My name's Adam Vaughan. I'm a director at JDK Architects in Newcastle. We're a medium-sized practice that's keenly interested in low-carbon design. I'm also co-chair of the RIBA Northeast Sustainability Forum. The forums were set up to help bring together professionals from the region to develop their skills and sort of share experiences in sustainable design. So as an architect practicing in the region, I've been amazed to see how the whole construction and development industry has started to gear up to meet the climate challenge. We've got a long way to go, but now clients are really starting to talk about the climate crisis. And my gut feeling is things are going to happen fast. However, it's fair to say that most people are still very much focused on the emissions caused by the operation of a building, and too many of us really overlook the emissions caused during a building's manufacture, its maintenance, and its dismantling. As you're probably aware, embodied carbon emissions are a key component of the RIBA 2030 climate challenge. And I'm sure some of the practices joining us today will have signed up to that challenge. The challenge really sets out a target of reducing embodied carbon emissions by 2030 by 2/3 in domestic buildings and by just over a half in non-domestic buildings. And meeting these targets is going to be just as difficult, if not harder, than those for energy operational energy consumption. As a practice in the Northeast, JDK have been looking at embodied carbon tools over the last 6 months, trying out those that are available. So it's timely that we have Mark Goodbrand from Elliott Wood here today to share his expertise from a structural engineering perspective. Elliott Wood have developed their own carbon tool for analysing the carbon embodied in structures. And I'm pleased to say it's just been accepted by the Institution of Structural Engineers and is being made available to all engineers in the industry. And this excites me for two reasons. Firstly, a building structure and substructure is responsible for such a large proportion of carbon embodied in a building, particularly associated with steel and concrete. But secondly, our industry's response to the climate crisis must be collaborative. Architects and engineers have a long history of working successfully together, and we must continue to develop these close ties to effectively drive down carbon emissions. I'm sure you'll have questions from Mark that come to mind as he presents the work that he's been doing. So please leave your questions in the Q&A chat box. I'm going to pick those up as we go along, and we'll have an opportunity to put those to Mark at the end. But without further ado, let me hand over to Mark Goodbrand. Mark, over to you.
Hi everybody. I think that's working. Thumbs up. Everybody see that? Yeah, good. Sorry. Yeah. So hi, I'm Mark Goodbrand, and I'm going to talk to you today about structural engineering and how we look at embodied carbon. Just moving the presentation on. To move. Hold on. Sorry. Presentation to move on. Oh, there we go. Sorry, moving on very slowly. There's a photograph of me pre-pandemic. See if you can spot the difference. So a little bit of history. I work for Elliott Wood. I'm a director at Elliott Wood. We are an engineering practice, 25 years of experience. I've got 20 years of experience myself, working largely on listed and existing buildings, specialised initially starting in Manchester, working on various projects of converting mills and warehouses into city centre flats and accommodation in the late 90s, early noughties. And then moving down to London, working on interesting building stock where we looked at lots of city centre structures, and we really specialise in understanding the materials that buildings are put together with, and the constraints of those materials, and how you can use and understand the strength of those to enable a client to maximise those sites and assets. So yeah, it's a really key part of our job, is understanding materials and their strengths. As I said, we've got two sort of locations. We work in Nottingham, and we have two central London, one in Wimbledon and in central London office, and we have recently published our manifesto, which is our way of looking at life, which tries to encapsulate our idea of trying to engineer a better society. So we've split up what we think are the major concerns in our industry into 6 broad pillars, which have given us a framework for helping us to understand the modern world and allow us to look at things slightly differently. So this is what we call ethics, and that's been split up into different headings of education, technology, health, infrastructure, culture and sustainability. And we tried really hard to look at life from a slightly different view and explore themes within these pillars rather than the traditional sectors of the industry. So for example, looking at housing and the talk about housing, the housing crisis, which is bandied about quite a lot. And is there really a housing crisis when there are more beds per person in the country than there have ever been in the history of the country? Is it just that is there a housing shortage, or is it just that all of those houses are in the wrong place? And also looking at infrastructure, the desire to create big transport circulation routes, HS2, and big super train lines that take you super fast from one part of the country to the other. And do we really need those things when and this was written pre-pandemic, but when actually what we need to be able to transfer is data and information, because we're all proving quite well that we can work remotely from each other. We don't necessarily always need to be sat next to somebody to be able to work cohesively with them. And we work then to one of the things that we've done to try to put that into practice, the manifesto into practice, is we've built our own co-working space for consultants within the built environment. So we operate the Building Society, which essentially is a space where consultants can come and be have a membership, and we have QSs and architects and engineers all sat side by side, working collaboratively, feeding from each other, getting work from each other, which is really helpful, but also learning more about each other. And one of the requirements of being part of the membership is that you take part in a rolling program of education, of teaching and talking about your own practice and the latest things in your industry, which is a really exciting place to be working. So what are we going to talk about today? We're going to talk about what is embodied carbon, how do we calculate the embodied carbon in our structures, and also look at things like how we're performing already and what should we be doing with all these calculations that we're pulling together. So let's just look at what the problem is. Well, when you look at some of these very quick facts, the construction industry accounts for approximately 60% of all UK material use, and a third of all the waste that is produced in the country comes out of our profession. So the built environment contributes 40% of the UK's total carbon footprint. And then, I mean, this is the big one for me, 50% of that embodied carbon is tied into the structure. So this is quite a key fact. I mean, this is one of the things I think a few years ago that really got to us as structural engineers, because we realised that unwittingly we'd kind of found ourselves at the centre of quite a significant problem, I don't think any of us thought going into structural engineering university 20 years ago, or whatever, that we would end up being at the centre of this. But it turns out that a large part of everything that we specify contributes significantly to the problem of climate change. And as engineers, we're very comfortable with calculations and CAD and that, but we have to get better at talking to clients and informing clients about key decisions, because we don't want to be in that position where in what we thought was going to be 10-15 years time actually is rapidly approaching, where somebody turns around and says, actually you guys are the baddies, you're the villain of the piece. Why were you doing this? Why were you specifying buildings in concrete? You should have been telling us to build buildings in timber or whatever. And so we decided to try to get a handle on this and build some tools and some diagrams and better ways of getting across the importance of the decisions that clients were making, so that they didn't just make decisions based on cost, which seemed to be, as we all know, seems to be quite often the determining factor in building specification. And then this is also a really important one, which Adam referenced before, 51%. It's roughly 50-50 split between embodied carbon, so that the carbon in a building, and the operational carbon. And as the national grid becomes more sustainable and less focused on production from fossil electricity being produced by fossil fuels, as we've seen, in the last 12 months, there's been a rapid change with sustainably generated electricity starting to overtake fossil fuel burning. That percentage of operational carbon starts dropping, so the percentage of the embodied carbon becomes more significant, and so we really do need to do something about it. So what is embodied carbon? Well, effectively, it's carbon is a shorthand for the total greenhouse gases emissions through that are released into the air. So that covers methane as well. But in the construction industry, this is the emissions that are generated to produce the built assets. So how much carbon is released from the extraction of the material from the ground, what goes into the manufacturing process of it, transportation, so that getting it on the back of a lorry and taking it to site, putting it together, and then what happens to it at the end of its life and its reuse. So with our understanding of materials, we're able to plot this out, and we know where we know the history of materials. We know that concrete comes from extracting Portland stone from the ground. That's then taken and heated to huge temperatures with a huge carbon cost to create cement. That's then in a hugely inefficient methodology with blast furnaces that release lots of emissions. Then that's transported to site and then erected, and then after 50-60 years building life, buildings are demolished. Concrete isn't very good at being recycled and is often downcycled, so it gets crushed and it gets reused as things under slabs for MOT or build-ups, and isn't able to be reused again. Steel, similar process. You have to excavate from the ground, and then you have to raise it to a huge temperature to melt it, and then form it into useful sections. Then that's carried to site and assembled, put together. Slightly easier to demolish if done properly, but generally it just gets cut on site and taken apart and pulled down and then melted and recycled. And timber, the only one of those materials that actually absorbs carbon before you even get to it. So before you even cut down a tree, it spent all of its life absorbing carbon and sequestering the carbon. You then take that to be processed, carried to site, and erected, and then it can be burnt at the end of its life. It can be recycled, or it can be reused. So these processes and these sections of the life cycle of a building are clearly defined in the RIBA guidance note, and we have a fair understanding of how what they contribute at each stage. Just circling back on that point about the timber, is that the current guidance assumes that you're taking timber which is already sequestered and taken all of the carbon from the atmosphere in its growing, and then it currently assumes that at the end of its life cycle that it is then re-released back into the atmosphere, which is a quirk of the way that we are currently measuring the carbon involved in timber buildings. So it's assuming that it's at the end of its life that it either gets sent to landfill, gets sent for it then whether it's burnt or sent to landfill, it releases methane, which is 20 odd times more, contains 20 odd times more than it would do if it was just left, and then the very small portion of it is actually directly reused. So which are quirks of the way that we're currently required to measure carbon. So how are we measuring carbon internally in our own projects? Well, we developed a tool. We developed the framing tool, which is a very quick way that we will take a structural grid. We'll get architect's plans, and then we'll apply a sort of structural grid to that. We can apply loadings, whether it's office, live loads or resi, and then we have a tool that we can push and pull, and that generates a series of framing options very quickly. It's really useful for standardizing bays and buildings. Clearly that's not always the case, and not every building is square, but it gives you a really good starting point, and that churns out structural solutions in concrete, in metal deck and steel, or CLT and steel beams, or even CLT and glulam. So it's quite a useful tool for getting multiple options of how a building might be structurally framed. And we also have the database, which is a big database of all of the carbon costs of various materials that are used in the construction industry, which is a live database that is constantly being updated. So we use those two things. We then we get all of this information from the RICS professional statement, which tells us how to assess the whole life carbon of buildings. And it's a way of standardizing the way that everybody is counting these and calculating the carbon cost of these elements. One thing that we don't cover in the tool is the building in use, which is that occupational carbon that we talked about at the beginning, but we try to cover the rest of the emissions for the project. And so over the years we've become very adept at modelling buildings. We use Revit on pretty much all of our projects, and often find ourselves, because of the type of work that we work on, which is largely existing buildings or complicated sites, highly constrained sites in city centres, we will very quickly Revit the existing arrangements on site, so we'll find out where the tube tunnels are underneath or the railway lines next to the building. We'll draw those on as constraints, but also we get hold of archive information really quickly, and often before an architect has even decided how a building is going to be altered. We will have got hold of building control information or archive information, use that in combination with the measured survey, and we will generate Revit models of existing buildings. So we're really good at using Revit as a sort of sketch tool rather than this really fancy. I mean, some of these are quite late in the design process and show how we've integrated lots of services, but they start off as sketchy models. Just because they're not hand drawn doesn't mean we can't sketch in Revit. But you get a sense of size and quantities very quickly. So we use that as a tool. We then start Reviting some of those structural options and grids that we got from the structural tool. And again, this is all sort of stage 2 work, RIPA stage 2 work, multiple structural framing solutions for one scheme, which we would be using to coordinate with the architect and see that we've got the right floor thicknesses and column sizes and things like that. And then we use that with the Carbon Revit plugin, so it connects directly back to the database that we've got on our server, and then we use all of these things in combination. So the database, the framing tool, and our Revit drawings to start producing some outputs which allow us to put each of those structural framing solutions side by side at every design stage. We can tell our clients that the RC option, when we split it down into substructure and superstructure, contains a certain 100,000, or 5,000 tons of CO2, and an alternative in steel and CLT slabs might be half of that, which is quite a useful way of putting that visually. We tend to do this with all the different frames. Now that's quite easy. That's quite useful to compare the structural solutions for each one of those for your building. But we need to know how does that compare, and so you've got them side by side. Well, so this is a new build example for us, but here's a residential project that we've got in up in Sheffield that we're currently working on, and we have looked at the different options. We've expressed the way that you express the carbon count of a building rather than the total carbon in a building. It gets expressed as a CO2 per meter square, so tons of CO2 per meter square, which allows you to standardize for different sectors of the industry what is the norm and what is the average and carbon count for that type of building. And so this is a residential building. We've put on here a dotted line which reflects the 0.2, which is the carbon targets that have been set for by LETI, the London Energy Transformation Initiative, for 2030, and obviously for 2050 that would be at net zero. But we've got two alternatives here for the CLT, which is the mass timber panels that we'll be using. One which assumes that the building is designed for reuse, and one which assumes that the building is follow the RIBA guidance and assume that timber has been burnt or sent to landfill at the end of its life. And even in that instance, we're still getting a result that has a lower carbon count per meter square than the other solutions, which we've looked at: precast concrete panels on steel frame, RC frame with cement replacement, or a steel frame and composite metal deck. Interestingly, on this project, all of those solutions get under the 2030 target, but really the only way that we'd ever get to net zero is by challenging the way that we look at the end of use of timber. And we think that's a really interesting thing to be exploring, because building design lives for a building that's designed has a 60-year design life, are we really saying that in 60 years time, so in the year 2081, are we going to be allowing buildings to be demolished and thrown away in the same way that we do now, or will the industry have changed as it needs to the point where every building material is no longer thrown away or downcycled, but is actually taken down and dismantled and reused for another project? So that's quite an interesting way of comparing the structural solutions and their impact. So as I mentioned before, the London Energy Transformation Initiative has rates that it expects buildings to be achieving on that roadmap to getting to net zero, whether you're in residential, commercial, or office or school. Then there are kind of business as usual. These are the kilograms of CO2 per metre square for a building of that type currently. Typically, what it needs to be as the decades move on to get to the 2030 targets, it needs to be cut in half. Well, almost a 65% reduction from that baseline, and obviously it has to completely reduce by 2050. And then I think this is just more slides which try to demonstrate how you can split it up and see where the carbon count is within the different parts of a building. And so we've been able to take all of that information and look specifically at the carbon count of the structure, and so we know out of the embodied carbons for schools, which for 2030 needs to be at 600. We know that for a school it needs to be the school structure needs to be 199, so nearly 200 kgs of CO2 per metre cubed. And then we've been splitting that down even further. This is just another slide which pretty much says the same thing, but we've been using that then because we've had our carbon tool now operational for almost 4 years, and we've been collecting the data on all of the projects that we've been working on for internal use and kind of grading them, and then we've created a leaderboard within the practice to see which of these projects that we're working on are hitting the targets, which ones are reducing the carbon by the most significant amount. And the reason we're doing that is because we're not entering into we're trying not to enter into design choices with pre-made assumptions on what is a good or a low carbon building, and so it's not trying to tell straight away what or have an agenda that timber is the right thing. It's trying to understand what is the right thing and what are the patterns and what leads to lower carbon counts. So we've got this leaderboard which helps to pull together all of the buildings that we're working on in the practice, and all of our engineers are encouraged to constantly update these with the new projects they're working on, and we do carbon assessments at the end of every design stage, and yeah, so we've got these various metrics that we use to say where your building is on that journey to getting to net zero. Other things that we think about when we're building is more locally the emissions that the construction industry releases. So we know that when you take those volumes of If you're building a school, for example, you take those volumes of the structural concrete. We know that a concrete wagon carries 6 meters cubed of concrete, so we can very quickly work out how many vehicles will be running along those small roads and residential roads leading up to a new build school. We know that the volumes of the timber and steel, and we know that a flatbed lorry can carry a certain limit, and therefore has a bigger capacity for taking a larger floor plate. If you designed a building in CLT and steel, then you could minimise the number of vehicles on the road, but approaching the site throughout the 12-18 months of construction, and therefore minimising the amount of fumes that are locally released off the roads. Just interesting ideas, and we do that again with all of our buildings to look at vehicle movements. And this is often something that we information that gets fed into the planning, design and access statements that help to show that we're trying to mitigate the impact of the construction on local environment. Concrete is an incredibly versatile material, and one that we have fallen in love with in the middle of the last century, and almost built everything with. Kind of gone out of fashion architecturally, but increasingly those modernist, modernist buildings, mid-century buildings have come back into fashion, and we are adapting and reusing them. But there's no getting away from this material as an incredibly strong and versatile material, and so often tops the list of the material that we end up specifying and choosing to build our buildings from, particularly when there's other issues, which we could probably have a whole seminar on, related to fire and acoustics surrounding timber buildings, which are not insurmountable, but also challenges in themselves. And so what can we do to concrete to help make that more environmentally friendly? Well, there are a couple of things that you can do. You can specify GGBS, so ground granulated blast furnace slag. So this is the byproduct of the steel industry, material that can be put into concrete as a cement replacement, and we can specify 60% of 50 to 60% of GGBS in structural materials. Is higher, I think, in foundations. You can go much higher in piles. It does have an impact on curing times of concrete, so it slows down the time concrete takes to go off, and so causes longer, not delays, but causes construction periods to elongate. And we can specify these things to, if we have to go down a concrete solution. It's worth noting that GGBS, being a byproduct of the steel industry, is actually still reliant on blast furnaces, the huge temperatures that are reached to melt steel, and in the UK all of those furnaces are powered by fossil fuels. There are electric arc furnaces on mainland Europe where you could argue that these things could be done with more sustainable energy generation. However, there's a transportation issue associated with bringing steel in from another country or from mainland Europe, and so that you end up tying yourself up in knots with what the right thing to do is. But also you should remember that without these the production of steel, then this material wouldn't exist, and also it's in very big demand. So America and China have woken up to the use of it, and so there isn't enough GGBS GGBS in the world currently for the construction industry for everybody to use this material, and it's in very high demand, and therefore the cost of it rises. So it comes with its own challenges. So what have we learnt from everything that we've been compiling and reviewing and looking at? Well, a few sort of headlines that have come out and stick out quite frequently is that we need to be trying to avoid basements and retaining structures where we can. It's very difficult to build these things in a sustainable material, and often you need piled walls or reinforced concrete walls to build basements, and so it's very difficult to build a basement without impacting the carbon count of a structure. So one of the key decisions you might make very early is do I actually need a basement with my building? We should be trying to eliminate new piles. I've got a building on site currently in central London where we've got 45 metre long piles, where they are currently 900, about to move to 1.1 metre diameter piles. So there's a huge volume of concrete going into these piles. So we need to try to either understand what the buildings on these sites have been built from before. Is there an opportunity to reuse piles? We've become very adept at of testing and understanding the capacity of existing foundations. So can we reuse these on our site and just play around with our new build grid above to only load these areas, or provide some transfers? Lessons learned from superstructure. Really, we need to learn how to reuse existing structures wherever possible. This is an incredibly important point, and I think something that's increasingly going to become part of planning requirements. They'll be much tighter, and we're finding it in some London boroughs, much tighter justification required for the demolition of existing structures. We need to start thinking about buildings as, you've probably heard this before, but buildings and material banks. So we're getting to a point where we're not mining the earth for materials, but we're mining existing buildings and getting a good recycling market going for materials. We need to be learning how to use less materials and don't over-specify. We get accused of over-specifying quite a lot as engineers, but and interestingly, this is a bit of a dilemma as well, because the reuse of existing buildings, often you're trying to find what the capacity, the unused capacity in a building is, so that you can justify adding another story or two. How can I get away with 2 stories on top because the engineer in the 1950s over-designed it, or the spec was over-designed, and that kind of is at odds with this idea of wanting now to move forward to a much leaner design, where there isn't very much capacity, and you're operating at 97% of the capacity of the materials that you're using. We should use fewer materials, so don't over design. Even if you're designing a building in timber, don't the idea the still try to get your section sizes as small as possible, because we need to be building less rather than more, and even with timber. If you do have to use concrete, then try to use cement replacements where possible. Try to design lighter facades. So a lot of structural sizes are not defined by the weight that they're carrying, but the amount that they move. So can we design facades to be more flexible, so that we don't have to have such tight deflection tolerances on perimeter structure, which would allow us to relax the volume of the material that's being used there. Lighter facades. I think another thing that needs to be done, we need to be looking at reviewing live load allowances that we have for buildings. I've got a little slide next which is quite interesting, because when you see what live loads allow for in offices or in resi is a phenomenal load, and is that load ever really realised is an interesting point. We should be looking at reducing column grid. So there is a big push. We get pushed by developers, largely led by agents, saying, "Oh, we have to have a 12 by 9 metre grid on this new office building." You'll only be able to let it if you get a completely column-free space. Is that real? Is that a real requirement? If you bring structure together and closer together and have more columns, then you can reduce this. It's an exponential reduction in the beam sizes and the floor thicknesses, just for accommodating a couple of columns or a tighter column grid. Interestingly, you see buildings in the east of London where brickwork's exposed and timber's exposed and parts of the existing building are left exposed, and this has given people character and given the building character, and they're incredibly attractive, and people enjoy working in these buildings rather than in these sort of sterile spaces where everything is the same. Can we bring some of that into the central markets, bring that sort of idea into the middle ground of office design? And then I think we should be specifying, whilst I'm saying that's not my agenda, we should be specifying or trying to find ways of specifying timber now to help lock in carbon the more. So if we cut down a tree, then that tree, if it's from an FSC accredited forest, then that's replaced by another one, and over its lifespan it will continue to absorb carbon, which is a hugely positive thing. We need to be doing that now because there's a climate emergency now, and we need to be reducing carbon emissions now, and offsetting that by planting trees is a big one. Just a couple of practical examples. So this is a building which just got practical completion today, I think. So this is the Forge in Woking, an EPR building, a concrete frame building from the 1990s, which was unoccupied, and we have worked with Hawkins Brown to we've rationalised all the plant in the roof. We've created a huge open plan office space at roof level, with a few stray columns here or there. We've created a lovely new entrance. We've infilled the atrium and added something like 30 or 40% onto the floor area of the building. And when you do a carbon count on that, rather than demolishing and starting again, we've given a building a whole new lease of life, and that area of town will have an occupier and continue to function in a very modern looking office, all for 39 kilograms of CO2 per metre square, which is 39 kilograms of CO2 away from net zero, which is a hugely big win, so that you can see the advantages of reusing existing building stock. This is the grid on the right here, in the middle, just trying to illustrate what certain things that we're allowing for. So this plan shows the imposed loading conditions for comparison. So when you look at this sort of this bay here with the desk offices, the load of those tightly packed desks, something that looks like from a Douglas Coupland 1990s microserves setup. We're currently allowing, we're designing for 2.5 kilonewtons a metre square, plus another 1 for partitions. But actually, when you add all that up and divide it by the area, it's only 0.5. So significantly less. Look at the all of these elephants in this tightly packed grid. This 9 by 9 grid is 3.2, so that is less than what we're currently allowing for offices. These dots on the screen are people, so this is 2.8 kilonewtons per metre square of people in a 9 by 9 grid. How tightly you have to pack them. And 2.8 is only 0.3 higher than what we're it's 0.3 higher than what we're designing offices for at the moment. Why are we doing this? It seems like we're over specifying floors, and the higher load that buildings have to carry, the bigger the structure has to be, and the more carbon that goes into them. So it's a really obvious win to get them down. So we are counting carbon, but what do we need to do? We need to learn from it, and what do we do next? Well, I think this is an interesting diagram, and it's one that ties into some of the things that I've been doing from working on listed buildings. You know, we need to understand how buildings are working, and we need to start from a position where we're retaining existing structure, where we can reuse the carbon that's already been spent. If we can't do that, we should be reusing materials on site, and if we can't do that, we should be reusing them off site, and then as a last resort we should be removing them and recycling them. So this is the idea of the circular economy, and using buildings as material stores, as Lego bricks, and we're doing this on a couple of projects now. We've got a research project with Grosvenor Estates, where we're working on a project called the Most Sustainable Building, and they want to build they want to adapt a site. They've got a series of buildings that they know that they want to demolish, or they know past their function, and so we're using those as we've audited pre-demolition audits of all those building materials, and they're used as Lego bricks to build a new building from. Sorry. We've also got this idea of zero waste, and we've got projects where we're not taking anything away from site, and we're reusing everything on site, where we've demolished a row of garages, and the precast concrete is being used as new foundations for homes, timber homes. Lots of interesting ideas. Recommended reading. You should definitely be reading these documents to understand how to count carbon and measure carbon better. And then, as Adam said earlier, the carbon tool will be launched on the 18th of March, and the idea is that we have made a very simple tool that we're encouraging architects to encourage their engineers to use. It's a very simple, free, easy to use tool, because I think we believe that we'll have much bigger impact on the environment by getting every other structural engineer to be doing this than simply keeping it to ourselves greedily and being one of only a few, central London practices that can afford to have the resource to generate a carbon tool. Will have a really small impact, rather than getting everybody across the country using one of these things and telling their clients what the impact is. There we go. How am I doing for time? There we go. I think that's the end of my presentation.
Thank you, Mark. No, that's really good. Faye, am I back online again? Great. Yeah, thanks, Mark. I mean, that was really interesting. A great overview of the challenges involved, and particularly looking at some of the details around things such as sequestration of carbon and timber. Eco steel. That's hot topic at the moment, particularly when we look at the coal mine that's proposed for Cumbria, and concrete as well, and all of that without even covering the thorny issue of cost, which is probably opening another can of worms. I was reminded, as you were talking, particularly about timber in buildings, of something that Jane Anderson from Constructing LCA said to me, which was that we need more buildings with timber, not more timber in buildings. And that really sort of flags up some of the really interesting issues you've raised there about efficiency and about waste. So I'm really pleased that you've covered that. We do have time. We've about 10-15 minutes for questions. As host, I have the pleasure of kicking off. I'll abuse my position here and ask you the first one. And one thing that's really interesting to me, and obviously you're speaking from the the viewpoint of I suppose an engineer dealing with quite big buildings, in the capital and elsewhere. But for architects all around the country who may be working on a bigger range of projects, what do you think we should expect from our engineers in the near term when we're discussing embodied carbon? Should we be expecting our engineers to be able to have these sort of knowledgeable conversations at a relatively early stage, as you seem to be doing?
Yeah, I think so. I mean, we work on big buildings, but we work on a massive range of buildings, and we're doing Mrs. Miggins's side returned extension, as well as working on these big things all the time, and it's about design challenges and interesting architecture. That's why we get involved in buildings. But we are now, even on those sort of domestic scale projects, we can calculate quickly from the hand sketches some volumes and start reporting on the carbon. And we do it from an early stage, so we should, we should start getting very quickly to a position where you should be encouraging all engineers to report on it at each design stage, and because the QS will be reporting on the cost, and so we need to be also reporting on the cost of the environment simultaneously. And I'm not saying it absolves us of the decision making, but it's much better that you're presenting the client with this information and they're making the decision, rather than it makes it easier for well, it doesn't make it easier, but it becomes a more prevalent point of note in the meeting.
Absolutely, yeah. And there was a question that's been raised by Jack, which he's talking about the ECF, which I presume is sort of embodied carbon footprint of steel. And it sort of echoes a question that I had in my mind, which was about the data set that you're using. I think you did touch on that, but perhaps you could elaborate about, because obviously there isn't really, I mean, there are various data sets out there for embodied carbon, but and then there's the whole issue of EPDs as well, which is sort of slowly gathering steam. So perhaps you could tell us a little bit about the data that sits behind your tool.
So most of that comes from the the document that I put in as further reading. So it's the RIBI guidance notes that pulls into the tool there, and I think that is a live data set. So it's not something that we've put in once and just sits there. It's constantly being updated. So as we learn more about these things and start to realise what parts of these materials are using carbon and what parts aren't.
And presumably, as industries, particularly sort of steel and concrete manufacturers, start to reduce the carbon content of the materials, that will be reflected in those live figures that come through to your software. Yeah,
well, we know what the like I was saying with the percentage of GGBS used. So we know that cement will have a certain content, and as that reduces and is replaced by GGBS, we know what the overall then cost of the concrete is in terms of carbon. So it's breaking it down into the individual materials and then having a data set for each of those. Yeah.
I was intrigued when you were talking about the structural capacity of or sort of the load bearing capacity for imposed loads. And I suppose it does bring us, there's a whole issue around the regulation of structures, whether that's through building control or design codes. And I was interested that ACAN, the Architects Climate Action Network, recently launched their decarbonised construction campaign, which is very much focused around embodied carbon. And one of their proposals is for a new Part Z to the building regs, which would cover whole life carbon assessments, and I'm guessing that's probably following a sort of format to the sort of London plan that you're probably more familiar with. And I just wondered what your thoughts are on regulation of building regs and how quickly or otherwise we should be rolling that out.
It's not something I've thought about. I guess it's important that these things never become kind of box ticking exercises, and that you actually, if it was regulated in that way, it would be encouraging people to do to monitor and force people to doing these things. But often the assessments that we do, BREEAM or WELL or whatever, we're trying to generate buildings that are better for the environment, but quite often they can become box ticking exercises and sometimes counterintuitive. But so I'd be for it, but I think it would have to be in a way that actually offered real benefit. But I do think that there should be some review of the live loadings that we're allowing for our buildings. It seems crazy, and the BCO guidelines go over and above what the live load, the Eurocode requirements are for buildings, because they think that's what developers or office tenants want, and actually I think what office tenants want is probably is constantly evolving, and they would rather have a building that's better for the environment than columns that were 12 by 9 meters apart. I think that's changing.
Sure, sure. We have a question here from, I think it's Suhaib, a postgraduate researcher, saying, do you consider the impact building design and specification will have on the carbon footprint of the contractor during construction? That's a tricky one. I think you covered it, I suppose, in terms of deliveries, but
it does allow for. I'm trying to think about this. So that it does allow for construction in the A4 to A5 category. There's allowances in there in the A5 category for site waste from the construction. So for different materials, and we know that the waste production from on-site or off-site construction is different, and I think there was a lack of data until fairly recently, but I think that is something that's been improved in the last 12 months. So yeah, it is accounted for.
Yeah, excellent. We've got a few questions which I think actually relate to the detail of your tool, and I'm guessing this is probably relating to the sort of early stage tool that you referred to at the sort of feasibility stage.
Yeah.
One question was with regards to two-way reinforced concrete slabs with downstand beams, more structurally efficient, and whether that was covered. And then also, is increased facade height associated with deeper structural zones considered?
Yes, I'll take the last bit first. So the deeper floors mean, this comes up in cost all the time. So deeper floors, structural floor zones mean taller buildings, and then therefore that means more facade. And so there's a rate per metre square on elevation for facades that increase the cost of a building if you make it taller. So that's why we as structural engineers are always under pressure to reduce our structural zones, because it helps to get the cost down in that way. The tools work by looking at volumes of structure. So once it's drawn, the amount or the height of that is accounted for anyway. So, but it's the height of the structure that we'll be looking at. The facade itself is kind of a finishes element, so we're not counting that in our tool, and we'd expect that to come from the architect.
Absolutely.
What was the first part?
Well, it was the question was two-way reinforced concrete slabs with downstand beams are unfashionable but more structurally efficient. Is this covered by the tool?
The tool, the concrete tool will pull that up, and that will be an option that we can look at. And then, downstand beams are not particularly fashionable because we need to get air circulating through buildings, and they create pockets of air and cause problems with ventilation. But we live with downstand beams in existing buildings, and we core holes through them and do things like that, so we can make them work. But it is covered in if we design a building that way and we want to count the carbon, then we've modelled it in Revit, and so we have the volumes of concrete, and so that would be accounted for in the assessment. Whether that's more structurally efficient or not, I think depends on the building that you're building.
Excellent. Okay, brilliant, Mark. Well, that's been really interesting. I think we're going to draw it to a close. We're getting perilously close to the end of people's lunch hour, so I don't want to abuse that. We'll wind up. But just Faye, if you could give me the thumbs up to this anonymous question asked towards the end. Has it been recorded? Will the recording? So yes, it has been recorded, and that recording will be available. I'm guessing so. And is there a copy of the slides will be made available, Mark? Yeah,
well, it's quite a heavy presentation, so I will PDF it and send it over, and then that can be circulated afterwards.
Fantastic, and Faye can know that, sort of send that out to the attendees who signed up to the event. Brilliant. Okay, well, I hope there's been something of interest that in that for everyone who's been along to this event this afternoon. I hope that there are going to be some interesting conversations between architects and engineers on the back of that. We'll look forward to perhaps getting some feedback on those at upcoming events. Alice has kindly popped some links to upcoming events in the chat, so do pick up some of those. There's a couple of others I'm involved with, including the Sustainability Mastermind events, and it'd be great to see some of our regional architects present at that. Yeah, so it just leaves me to thank again Mark. Mark, thank you for your time today and your presentation, and best of luck launching this tool with your institution.
Thank you, thank you. I do recommend that architects encourage their engineers to grab a hold of a copy and start using it on their projects. That'd be brilliant.
That's fantastic. Lovely. Thanks, everybody. Goodbye now.